Okay, now we look at the VSEPR theory, and this is going to help you understand hybridization of carbon, right? So we're only going to look at what's necessary. You're not going to look at it as something beyond necessary, okay? Now, VSEPR theory, VSEPR, stands for valence. Okay, I forgot to put that. Let me put it. It stands for valence shell electron pair repulsion. Okay, repulsion. All right, that's what VSEPR stands for. It's an acronym. Okay, so we say the valence shell electron pair repulsion theory, or we can just say the VSEPR theory or the VSEPR theory. Okay, valence. You know that the valence shell is the outermost shell, right? Is the outermost shell, the outermost energy level, right? We've gone through that. The shell, the difference between shell, subshell, and orbital. It helps. So valence shell is the outermost shell, and we are looking at electron pairs that are in the outermost shell that are repelling one another. Okay, so here's the idea. Here's the idea, and what we use it for. Don't even make it out. This because this VSEPR theory is what helps us know the shapes of our compounds. Okay, the shapes of our covalent compounds. So we have things that have covalent bonding here. Okay, and we're going to use this VSEPR theory. And what it says, here is the idea. It says electrons are negatively charged. We know that all electrons have the same charge, right? So because of that, because electrons have the same charge, we know in chem we say like charges repel, right? And unlike charges attract. So like charges repel. Now what we say is electrons are negatively charged, right? So these electrons are going to repel one another. Okay, they will repel one another. But remember that two electrons will be in an orbital. So that those two electrons will repel each other with electrons in another orbital, right? With two electrons in another orbital. So they'll be repelling each other, right? As a result, because they are repelling, they are fighting each other, they are pushing each other away. As a result, they are going to spread out as far away from each other as possible. Remember this, orbitals are going to be as far away from each other as possible. Are you hearing this? Yes, electron pairs are found in an orbital. An orbital will have two electrons, right? Good, and you know what it is. So these orbitals are going to repel each other as far away as possible. So all the time, when you see it, it's going to have, they don't just take up any position. No, they take the positions that make them as far away from each other as possible. And this, if they are far away from each other, there is less fighting, and we have less energy in this thing, and we have stability. Okay, we say we have stability. Okay, but if they are close to each other, there's potential energy. They want to fight. They're building up. So yes, that is what it is. So what is the idea of VSEPR theory? It says electrons are as far away from each other to minimize repulsion. Okay, and that is what we use to explain the different shapes, because VSEPR theory helps you know the shape. It says we know that if you have this number of electrons or orbitals or atoms close to your thing, then we know the shape. We know the shape. Okay, the shape is going to be like this and like that. Okay, so here we are saying, right, so this is what we use to determine the shape. So how do you then determine the shape? You look at the number of electron groups that are around your central atom. Okay, the number of what? Of electron groups, the number of electron pairs, the number of orbitals. Okay, whether they are bonding. So a bond has an orbital, right? Because bonding comes from the overlapping of orbitals. You can look at the valence bond theory. Okay, it's in one of the videos, maybe the next one. The valence bond theory helps you understand what? That every time you have a bond, then you have orbitals overlapping, right? Good. So here we said you look at the number of electron groups that are around your central atom, electron pairs. And these could be an atom, right? So you could look at an atom, because in an atom you definitely have a bond there. So we can count it as an electron group. Those are two electrons together, right? Now, we don't care whether the bond is a double bond or a single bond or a triple bond. It's going to be the same. So you look at an atom. Atom, you treat it as an electron group, or we can call it an electron domain. Or you can look at a lone pair, which we are not going to focus on, okay, or electron pair. These things, if they are there, I'm going to show you with diagrams and it's going to make sense. These things, when they are there, that is what you are going to use to know the shape that is going to be the number of electron groups. You look at the what? The number of electron groups, and you're going to know the shape that your molecule is going to take up. The number of electron groups that are around the atom you are analyzing. The atom you are analyzing. You'll see examples. Here is the guidelines. This is how we draw. Now, what you must know is these things are in reality 3D shapes. They are not 2D shapes. They are 3-dimensional shapes because they are somewhere in space, right? This is happening in space, so it's 3-dimensional. And because it's 3D, that means one is the axis that goes like this, horizontal. The other one goes up or down. The other one goes inside and outside, right? Inside and outside. It's another one. So these guys, and they are 90 degrees apart. They are 90 degrees. This one, and that one. There is a 90-degree angle here, 90 degrees, and there is a 90-degree angle here, 90 degrees, and there is a 90-degree angle there, 90 degrees. So these are all 90 degrees apart. These are the three. One goes inside and outside, the other one goes left or right, the other one goes up or down. So, but our paper doesn't have that. Our paper can only go up or down and left or right. It doesn't have inside and outside. So how are we going to represent that? We use these guidelines. This is how we draw the 3D shapes. A solid line means that it is in the plane of the paper. In other words, it is either going up or down or left or right. Okay, we can combine up or down and left or right with a slanted line, right? A slant, it means it's just going up or down and it's also going left or right at the same time, right? Good. So but it's in the plane of the paper. But when you see this a wedge, it means it is coming out of the paper. When you see broken lines, it means it's going into the paper. You say, what if I forget? What if I forget that broken line is into the paper and I think broken line is out of the paper? It doesn't matter, okay? Just know that wedge and broken line are for the inside outside, okay? Inside outside. It doesn't matter which is which. Now let's go to draw some shapes. Here's what we do. So first, what would happen? We are looking at now the cases. We are only going to look at 3 cases, frankly speaking, and we will be done. So don't make it harder than what it's actually going to be like. So our case one is when we have 2 electron domains, okay? 2 electron domains. In other words, we have 2 groups of atoms around our central atom, okay? 2 electron domains. Now, what is it going to be like? We have a central atom like this, and it is bonded to 2 other guys. That's what it just means, okay? It is bonded to 2 other guys. Remember, we said instead of a bond, it could be a lone pair, right? To say there is a lone pair. The lone pair was on A, and when we put it, we can say the lone pair is like this. But we are not going to work with the ideas of lone pairs today, okay? Right now, we're only just looking at what is necessary, and that is when you have groups of atoms themselves. So this could be whatever. What is the angle between? The angle between the bonds is going to be 180 degrees. That will make sure that B and B are as far away from each other as possible. The bond angle is going to be 180 degrees, and we'll call this shape linear. So whenever you see an atom that has 2 other atoms next to it, is going to have 180 degrees. They're going to be 180 degrees apart. Are you hearing it? Good. Now, case 2 is going to be, let's put our case 2. Case 2 is going to be when you have 3 electron groups, okay? 3 electron domains. Remember, when we say electrons, we're just saying something that is electrons. And obviously, these atoms have electrons. In this bond, there are electrons in this bond class, okay? And there are electrons in this bond. And those electrons are pushing out each other to be as far away as possible, okay? Those 2 electrons in this bond and the other 2 in this bond. So they push each other to be as far away as possible. So they're going to be 180 degrees apart, okay? And that'll be good. Now, K is for 3 electrons. So we have our carbon, central. No, it doesn't have to be carbon, whatever it is, okay? In this case, of course, there's going to be carbon for our case. But in this, we would have a central guy, and we have 3 guys. So this is going to form like a triangle, right? Can you see? And this triangle is in one plane because look, it doesn't have a wedge or that dotted line. So these are going to just be, you say 360 divided by 3, you get 120. So for 3, it's still easy. 120, 120 degrees. And we call that trigonal. Trigonal is from triangle. Trigonal, planar. Planar means it's in one plane. A triangle in one plane, right? This is the angles that these bonds would take to be as far away from each other as possible. 3 guys, right? Trigonal plane. Now, case 3 is what we care about because it's what's going to explain hybridization of carbon. Case 3 is when you are going to have 4 electron groups or 4 electron domains. Remember, electron domains means what? An atom or a lone pair, right? In this case, we are only dealing with atoms, right? So we have 4 atoms around our central atom. Let's put that. A, the expected one, everybody will be like, oh, I know this, I've seen it before. It's like this, where we have B, 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 B. And the angles are just 90, 360 divided by 4, 90 degrees, 90 degrees. I want to say, wrong. That is not it. I know when you draw methane and you're putting the expanded formula, yeah, Lewis, you do it like this. Well, Lewis makes you think, okay, this is the Lewis structure. It makes you think that, or the expanded structural formula. It makes you think that the bond angles are 90, okay? We still use them to draw, but what I want you to know is that the bond angles are not 90. They are actually not 90 in reality. You say they're not 90? Yes. What? So what are they? We actually now switch on to 3D. And this is what our 3D would look like. Let me show you. This is what our 3D will look like to maximize. So we are going to have our central atom. Okay, this is just easy. We have our central atom like this. Our A as our central atom. Then we put one will be here. And the other one is going to be here at an angle which is slightly bigger than 90, as you can see. Right? At an angle that's slightly bigger than 90. Then the other one, we represent it like this with a wedge. Then the other one, we represent it like this with that dashed line. Okay, the dashed line like that. Okay, so sometimes the dashed line is thrown getting bigger as you go out, or sometimes it starts big and it starts getting smaller as you go out. All right, you just look at which one your lecturer uses. I'll tell you. So here's the thing. This is going to be B and this is going to be B. Now this angle is actually tested and it is found to be 109.5, which is bigger than 90. So all this is going to be 109.5. Okay, the reason why I'm not putting it is because remember they are in different we can say this, they're not in the same plane, right? B is coming out, but you actually know that the angle between this is 109.5 here, 109.5 here, 109.5. They all form 109.5 with each other, with everyone. So between this dashed line and this B is 109.5 again. Okay, is 109.5. So all the angles are 109.5. Okay, there is 109.5 here. Okay, it's 109.5. That's why I'm not putting it, because I've drawn them in the same plane. You'd think it's not, but it is 109.5. Okay, so this is what it is, and we call this tetrahedral. So tetrahedral. So remember that when you have something bonded to 4 different atoms, listen, 4 different atoms, what is the bond angle going to be? 109.5. It has to be 109.5. It is bonded if it is bonded to 4 different atoms. Okay, bye for now. See you in the next video, where we now explain from here, from VSEPR theory, we now explain where hybridization comes from.